Hello, welcome back to the video lecture series for Introduction to Data Programming using Scala. In this video, we're looking at yet another type of linked list. We're going back to the singly linked list, but this time we're going to make it immutable instead of mutable. Now, this might not seem like much of a change, and you could write the code very much like what we did before, but there are some significant impacts that are going to occur because we choose to make this immutable. And in many ways, what we're going to do here is we're going to produce code that is very much like the list that you have been using since back in chapter 7 or something like that. It's basically one of the mainstays of Scala programming is the immutable linked list, and it happens to be a singly linked list. Now, to understand why we're going to do a singly linked list here, especially in the case of immutability, remember, being immutable means that you can't change anything about it. And one of our goals here is we'd like to be able to, in some way, add stuff and have it so that it's not slow. Okay? And in order for that to happen, we're going to make a few changes. First off, turns out, so with what we did previously, we wrote a list class that went around our nodes, and the outside world never saw the nodes themselves. For the immutable singly linked list, we're not going to do that. Instead, we're actually going to have the type itself is kind of going to represent a node in the list. And so you don't really keep track of head and tail, you just keep track of the first node in the list. Note that implies that you don't keep track of the tail at all. Part of the reason for this is because you don't want to be doing things at the tail. We kept our tail earlier because the append needed to be able to very efficiently add a node after here. For an immutable linked list, you cannot efficiently add a node at the end, because if I were to try to add a node at the end, well, that would have changed this list, which is supposed to be immutable, and I can't change it. The only way I can add something at the end is to make a whole new list and copy all the elements. So that's inefficient no matter what, so there's no point in keeping a tail to be able to do that quickly. It wouldn't help. On the other hand, it turns out that adding to the beginning just adds a new node, and you'll note that all of the rest of the nodes are intact. So this previous part of the list is still unchanged. Okay, so this is why when you could cons onto the front of a singly linked list, it was an efficient operation. We were able to do that with an immutable linked list. It's exactly how our linked list that we're going to write now will work. So I want to go ahead and create inside of our ADT package. We're going to make a new class. And I am going to call this the immutable SLL, going with we have a mutable SSL and a mutable DLL. So this will be our immutable SSL. You might ask yourself the question, the doubly linked list was much easier to write. Why don't we do this? Well, it turns out that because of all the pointers going around in this structure, you can't nicely make this immutable. And you can, but there's no efficient way to add to this structure in an immutable way. Okay? Any change you make here is going to change the list as a whole. So really, the immutable linked list needs to be singly linked, despite the advantages that we saw for our doubly linked list. Now, we're going to introduce a few things here, some of which are new. One is that I'm going to make my immutable singly linked list abstract. I'm going to take a type parameter a, just like we've seen before, and I'm not going to have it extend the buffer type, because buffer was mutable. I'm instead going to have it extend, let's actually just type in linear sequence of a. Import immutable collection.immutable dot linear sequence. Okay. Now, why are we making this abstract? Well, it turns out that we're going to need two different subtypes of this. And I'm going to introduce a new keyword here. The keyword is called sealed. And what this means is that you're only allowed to extend this class inside of this file. And I want that because I don't want other people to be able to make subtypes of this. I need subtypes of this class, but I don't want any old programmer to be able to make a subtype. So the only way to make a subtype is going to be to actually edit this file itself. You won't be able to add extra subtypes in other files. And that gives me control over exactly what subtypes exist. So I want to create two subtypes of this. The first one is going to be called cons. And so cons is also has a type parameter a, and it extends our immutable SLL on a. Okay. When we build a con cell, so and that's the term that is often used when you talk about these singly linked lists that are immutable. I need to pass two things. One is the data value that I'm using, and we just call that data. And the other is the next thing in line. Okay, because just like as I said earlier, this type here is just not going to represent a list wrapped around our nodes. It's actually going to represent the nodes. And so I'm going to call it next. And it is going to have the type of an immutable SLL of A. Okay. This has an error because it says, whoa, that needs to be abstract, or you need to put some methods in there. So if we go and we look in the API, I'm extending this linear sequence. Why a linear sequence? There are different types of sequences. The sequence type is very general. There are two subtypes of it, and we talked about this in a previous chapter, that give you information about it. One is the linear sequence, the other one's an index sequence. Something like an array where you can quickly jump to element 500. For that, you're supposed to use an index sequence. So anytime you find something and it's an index sequence, you know that you can do random access on it quickly. Okay. What we're writing, though, does not have fast random access, and so we're going to use the linear sequence instead. And the linear sequence, as it says up here in the comments, has three abstract methods that it relies upon. So we need to write these three methods in here, and the isEmpty, the head, and the tail, and those will allow things to work nicely. Okay, so we go back to our code. Not defined for method of length. Okay, and we will have to define a length in here as well. So def is empty. Well, this is a con cell. It has data in it, so the answer there is false. Def head. Well, head is supposed to return to us an A. It is supposed to return to us the data at this node, and, well, we called it data. And then def tail is supposed to return an immutable SLL of A, which should be the rest of the list, and so we pass that in, and that's called next. The error that we have here is still the fact that we need to override. All of these are going in place of the value, the ones in the supertype, so we still need to write a method for length. So how does length work? Well, obviously length returns an int, and in our singly linked list, we actually kept track of an integer that was how long things were when it was mutable. For the immutable singly linked list, we really don't want to have to do that. We don't want to use that extra memory because we'd have to put one not for the entire list, but one for every single node. Because basically, the list is a node. The head of a list is what you use for, or the head of the list is the representation of the list. It is a node. So instead I'm going to refer to this, I'm going to define this recursively, if I could type, so that the length of my list is 1 plus the length of whatever is after it. Oh, and this one's an apply method as well. Okay, so there's our length method, and in fact in the API, while it lists those 3 methods as the things that we want to write this efficiently with, we need to write an apply and a length because those are our abstract methods. So what about apply? So I want the nth element of here. And this is supposed to return a type A to me. Well, we're in a particular node here, and we're going to define this recursively as well. If the value n happens to be 0, you can think of this, the way we're defining this is kind of a recursive definition. Each one of these con cells is in itself a list. Okay, it's a sublist. And so when I ask for index n of a sublist, if the index I'm asking for is 0, well, that is the head of the list. So, well, actually, I can return head because I'm overriding that method. Else, well, what if it's not? Well, then it would be calling the apply, but calling it on the next element. And remember, I can call apply by just putting things in parentheses here. And so I'm going to call apply on n minus 1. Okay, and so that will go through to the next one, but with a 1 smaller index, boom, 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 and eventually get to where n is 0 or it goes out of bounds. Okay, so this is one of my subtypes for this. There's just one problem right now. If I only have a cons as the subtype, every one of these goes to a cons, and then they all have a next, and I can only have infinitely long lists, which, at least for this implementation, is somewhat problematic. So what I need is exactly what our normal list has. You'll remember there is a name that is given to a normal list when it doesn't have anything in it, and that name is called nil. Now obviously I don't want to overwrite their nil, so I am going to write my own nil, and my nil extends immutable SLL of A, except I don't have an A. So what can I put here? Well, what does this store? Nil doesn't store anything, so I'm going to say this is of nothing. And then this says, well, you still need these methods here. So what should these methods do? Def length. Well, the length of nil is 0. Def apply. What happens if you call apply and ask for a particular index? Well, at that point, it really doesn't matter what index you ask for. We are going to throw an exception on you. So we'll say into my nil. Illegal argument exception with an extra E in it is not happy. Oh wait, and I don't have a type A. We'll just go ahead and there. Okay. Technically that would be sufficient. It's also nice though for us to I'll just copy these so I don't have to retype it. For us to write these methods here is empty. Oh well, in the case of nil is empty is true. Head. Now for this I am going to copy that and say my nil has no head. My nil has no tail. And the type that I'm returning here, well, I'm just since I don't have A's defined, when you throw exceptions, the return type is nothing, which happens to be exactly the type that I made this immutable on. Okay, so we're getting close. How do I build a list? Well, I could try doing this with making a cons and passing it stuff all the way to nil. But there's another way that we like to do this. There's a syntax that we like to have when we're working with our singly linked lists. When you built lists most of the time, you would use this operator right here, right? I mean, this is how you built your list. The cons operator was what we did for our list when we want to prepend stuff to the beginning. And it doesn't change the original list, it just adds a new value to the beginning and makes that a new list. Okay. And that's exactly what I want to do here. I want to have this so that I can do cons, and I want to cons an element, and I'm going to say it's of type A, onto this list, and that should return to me an immutable SLL of type A. And so this will simply be equal to a new cons of the element that I'm adding and this, okay, whatever this might happen to be. Okay. Wow, everything compiles so far. It compiles nicely because I haven't done anything with it yet. Let's go ahead and let's start writing some test code. Test immutable SLL. Let's copy over our imports. That's interesting. Okay. Now, what I would like to do here is let's just write an at test and see if we can, okay, nil is empty. Assert true, my nil dot is empty. And if I could write assert Control Shift O, so we bring in the my nil. Oh, yes. This is our my nil. Shouldn't be a class because how many nils do we really need? My nil should be an object. Now we come back over here, and bingo, that test is happy. At test def list of 1. So I want to make a list that has one element in it. So I want to make a con cell of a new con cell, and I want this to take the value 1 and my nil. Okay. What's our error here? Not found type cons. Okay, that's an easy one. We're going to do that. Now we have another error, and it says these types don't match. Okay, why not? Well, because cons, in this case, it's inferring this is a cons because that argument is 1. It says, oh, you're doing a cons and you're building it with a type A, and that A is an int, so it says A is an int. So therefore, you have to have an immutable SLL of type int. And oh, wait, but my nil isn't type int, it's type nothing. And there's a problem. So to understand this, let's go look at something that you might not have paid attention to with list. Have you ever wondered why you can do something like this. So if I do 1, cons 2, cons 3, cons down to nil, I get a list of int at some point. Now what happens if I take high and I cons it onto res 0? Right? And if you had never played this with this before, you might go, oh, that's going to be an error. That's just going to crash. Oh, but it's not. It works. Okay. Why does this work? Well, because the list type is more flexible. Okay. Our buffers couldn't do this. Okay. If you made a buffer event, you couldn't add stuff to it that was of different types. You can if the type is immutable. Okay. And what this says here is that you're basically allowed to make a you're allowed to put other things on as long as they are well, the type that you get back is going to relate to the type that you append on. So if I had appended something, there are no subtypes of int, but if it had been something that was a subtype of whatever the previous type was, everything would have been happy and fine. But because I appended something that was, in this case, completely unrelated, well, then that means that it has to go all the way up to type any. What if the thing that I appended on was a double? Well, now I get any val. Okay? So it's picking the lowest common supertype of these things. How do we make our code do this? Okay? Well, to see how we make our code do this, I'm going to need to introduce a few new things. So one is an annotation here that says that the immutable SSL this is what's called covariant. Okay? And what that means is that, so normally when we talk about subtyping relationships, we talked about, so apple is a subtype of fruit. Okay, simple example. Well, did you ever ask yourself the question, is, say, let's do with the things we did before, is a buffer of string, is that a subtype, whoops, is that a subtype of buffer of, say, any ref? Okay. Now, string is a subtype of any ref. But it turns out that for buffers, buffer is not a subtype of any ref. And this is because buffer, when you just put an A here, what you get is something that is called type invariant. Okay? So regardless of the subtyping relationships between the type parameters, if your type is invariant, this will not be a subtype of that no matter what. So in the case of buffer, this is not true. But in the case of a list, it actually is. And the reason it is because this is listed as being covariant. Okay? Now, you'll notice here that this generated an error for me. And so it says covariant type A occurs in contravariant position in type A of value enum. Oh boy, what does that mean? Well, we need to add a little bit more information here, because note, just like with our list, when I added something of a different type to our list, the return type list was not the same type that went in. Okay? Whereas what we have here says, hey, I'm always going to return an A. I don't want to return an A. I might want to return something else, a B. Okay? And then the question is, well, and the thing that I'm consing on should be a B. But I need to put some restrictions on B. Okay? B actually needs to be not a subtype of A, but a supertype of A. Okay? I need it so that B can be any type that has A as a subtype, which is why over here, when I consed on a string, it didn't treat high as a string, it treated high as an any, because any is the common supertype of int and string. And so this will allow our cons to work. Now our immutable test here compiles, and we're able to cons this on. And I can also take and cons on using our cons operator on there. And we could write further tests, but this video is long enough for now, so I'm going to stop here and let you go off and write your own tests to make sure that our singly linked list there works. See you again soon.